Okay, the right way to start this unit is to get a few basics about the atmosphere. And when we did this class in a classroom, I would spend like 2 days on this study goal and the next one because there's a lot of interesting basics about physics and about chemistry um, that help us understand our atmosphere. And it's good for my students, I think, to know those basics. But now that we're in COVID, I just kind of got to give you the cliff notes. So I want to show you study goals 14 and 15. 15 doesn't have stars in your study guide, but I still want you to note something in number 15 as well. First, number 14, you should have this drawing from your book. There's like 6 things I need to point out here. Um, First, I want to clarify that our atmosphere has layers. You can see them labeled here on the screen. They're called the troposphere, stratosphere, mesosphere, thermosphere, and your book doesn't include one, but there's another outer layer on the very, very outside called the ionosphere. Now, the atmosphere is actually really, really small compared to the size of the Earth. If the Earth was a basketball, our atmosphere would be about 2 sheets of saran wrap. That's really thin. And actually, among those 2 sheets of saran wrap, almost all the chemistry that we experience, all the things that affect our life, are right at the very, very bottom of the first sheet. So we're going to be in apes almost entirely in the troposphere. That's where we live. The troposphere is from the ground to about 30,000 feet up in the air. We'll talk a little bit about the stratosphere. That's the layer above. That's where the ozone layer is. And then there's more layers above that, the mesosphere, thermosphere, ionosphere, that have almost nothing going on. The one thing I need you to add to your notes that's not on the screen is that each of these layers is very, very different. Very, very different. They have different temperatures. They have different amount of solar radiation. They have different ingredients. So in terms of chemistry, they're totally different environments. Things that happen in the troposphere cannot happen in the stratosphere. And likewise, things that happen in the stratosphere are not possible in the mesosphere, and so on. Each of these layers is distinct, unique, and separate. Number 2, you'll notice that red line, that is the temperature. First thing is the hottest place is the ground. You can see that temperature is highest at the bottom of the atmosphere because the heat source for our planet is the Earth itself. I know when I say that, kids think it's like the magma underneath the crust, and that's incorrect. See, heat has very low quality energy. It doesn't travel very far. So yeah, the inside of the Earth is very, very hot, but that does not heat us here on the surface. The magma thing on the inside, the lava ball that we're all sitting on top of, that does not heat us. The way that the Earth heats us on the surface is the same as my black sweater might give off heat if I was out in the sun. Because sunlight is absorbed and heat is radiated. So the sun is the source of the energy for our heat, but we are the source of the heat. We do an energy transformation. Sunlight hits the Earth and that gives off heat. So like if you move your hand closer and closer to a skillet, you'll get hotter and hotter until you touch the skillet and get burned. Same with the surface of the Earth. That temperature drops quickly as you get away from the ground. Then you'll notice in the stratosphere, temperature starts to rise again as you go out because there's weird radiation stuff happening. If you could notice on this graph, The stratopause is almost as hot as the surface of the Earth, and that's because weird radiation stuff. There's all kinds of chemicals doing gnarly things with radiation up there. Number 3 thing I want you to know is that gravity works on gases. So just like gravity is holding me on the surface of the Earth, it's also pulling the majority of gases down to the Earth. The only gases that can rise up are those that are more active. They're harder for gravity to hold. So what's interesting is the layers have different ingredients. Most of the gases are lazy, so most of them are down here near the ground because gravity works on gases. So again, if you look at this diagram, 90% of the atmosphere is in the troposphere. Almost all the gases are down here because gravity's working on it. That's why it's hard to breathe when you get to the top of Mount Everest, because most of the gases have been sucked below you when you're on top of Everest, because gravity works on gases. The only ingredients that manage to rise higher are those few gases that are very, very, very active. So you'll get a few gases here, and from here all the way out to outer space, that's about 1% of our total gases. Next. Well, one other thing. In that bottom layer where we live, the troposphere, that's where all the greenhouse gases are. That's where smog is. Basically, all the problems that we experience as humans are happening down in the troposphere, because that's where all the gases are. That's where everything interesting is. I should add that the only reason we talk about the stratosphere is because that's where the ozone is. Ozone is found higher up in the atmosphere above us, and that's good because ozone is toxic to us. It helps us as sunblock, but we don't want to be breathing it. Like sunblock is good on your skin, but you don't want to be eating that. Same thing. Ozone down here is toxic. That exact same gas, if we could get it higher up, would be helpful for us, but we don't want to be breathing that. So ozone is mostly found in the stratosphere, and that's a good thing because it blocks ultraviolet. That's where we want it, like sunblock. It's good up there. Block the sunlight so we don't get skin cancer. Funny thing is, that exact same chemical is pollution down here. So we'll talk about this in smog, but the same ozone that would have been helpful up high, when we make it down low, we poison ourselves. Smog makes us sick when ozone is down where we're breathing. So number 4 is ozone. We want it up there. That's where it mostly is. We don't want it down here because that's toxic. So it's pollution when we make ozone here. Observation number 5. Because we have ozone above us, each of these layers has different ultraviolet light. You might have heard of UVA, UVB. There's actually a UVC. People sell sunglasses with a little sticker that say UVA, UVB, UVC. You can see that on sunblock sometimes. UVC is gnarly. UVC is gnarly, gnarly, gnarly. Like if you were in full blast ultraviolet C from the sun, your skin would start to fizzle and you would eventually just powder away to dust. It's gnarly. If I were to take your funny looking body all the way up to the thermosphere, A, you would suffocate because there's no oxygen. B, you would freeze solid because it's so cold. And C, there's so much radiation up there, ultraviolet C, that your body would fizzle like dropping an Alka-Seltzer in water, and you would just go, and you'd eventually dissolve. Keep in mind, each of these layers is different, and there's funky stuff in those outer layers. You're basically in outer space, and things are gnarly up there. Ultraviolet B is mostly blocked by the ozone layer. So where we live down here, all we get is ultraviolet A. And that's like the pretty mellow ultraviolet. We'll talk more about UV light later, but I just want you to be clear that another of the differences in these layers is there's different amounts and strength of ultraviolet. We have ultraviolet A, a teeny bit of ultraviolet B, and that's it. As you go higher, you get more exposure to ultraviolet B, and eventually, if you go above that, you actually start to be exposed to ultraviolet C. That's why spacesuits are so gnarly. It's not just like keeping the human in, but it's keeping the ultraviolet C out, and that's actually pretty difficult because it's a gnarly energy, very high energy. Finally, you can see those little clouds. They're right there, little itty bitty clouds. And the thing I need to point out is that water on our planet goes up as evaporation, then condenses and it comes down. And each of those steps is a transfer of energy. So when you heat up water to make steam, those water molecules are carrying energy upward. And when those clouds come together and they cool off and they become rain, they have given heat upward. So fascinating detail is that our water cycle is a little wheel of heat energy being transferred from the surface to the upper atmosphere, because that rising water is taking heat in those water molecules. That's why they're rising, because they're gas, they're more excited, they got like extra energy. So you have excited water molecules delivering heat upward, and when they settle down and cool off, that heat is left behind. Water cycle moves heat energy in our atmosphere. You're supposed to know those 6 things for number 14. And for number 15, I didn't put stars, but I still need you to write something. I'm sorry. For number 15, I used to explain this at great length, but I don't have the time. So I'm going to put a red laser on the screen. I'm going to try to point some things out, okay? Our planet has an atmosphere that moves in these like circular donut shapes, kind of like a life preserver around the planet. There's this one, and that one in the northern hemisphere. And then there's 3 more in the southern hemisphere. You have to know their names. Okay, so it's polar, temperate, tropical in the north, and then the southern, tropical, temperate, and polar. See that here? And temperate is also known as Ferrel. Tropical is also known as Hadley. I'm sorry, you just got to know that. And those 6 donuts that are wrapped around the planet, our planet does 6. Different planets might have a different number. It's like a complicated answer with like how much solar radiation reaches the earth and how much water is here, but this is all in the troposphere. This is what drives weather. This is why you experience wind at the surface and why there's a different amount of wind up high. There's areas where the air is rising on average, like the equator, and where the air is dropping on average, like the 30s. That affects what vegetation grows on different parts of the planet. I wish we had more time. But one last thing that I need to explain is because of these dominant winds that push southerly, northerly, southerly, because of those winds, when you spin the earth underneath, you get currents. And if we had more time, I have like good demos for this, but I don't think the explanation would show up on the AP test. I just want you to know the names of the convection cells, and you probably would benefit from knowing the direction of these currents. North of the equator, it's clockwise. South of the equator, it's counterclockwise. You should know that. So this moves like a clock north of the equator and counterclockwise south of the equator. You should know that, because later on when we talk about El Nino, you're going to need to know that there's a current that pushes from the Americas to Indo. I know that's kind of random and thrown together. I'm struggling to figure out how to modify my class this year. But that's some basics about the planet that we're on, and now you know more about our atmosphere, and I'm going to stop this video.